Hello everyone, I hope you all are doing great. So today we'll be looking into the Mayer's relation. This specific terminology or equation is known as Mayer's relation. Mayer's relation. So today what we'll be covering in this whole video will be how this Mayer's relation is derived, what does each of the terminology actually mean, and what does make the CP in the positive form and CV in the negative form. So today we'll be looking into each and everything. Before delving inside the each and every factor, let me just quickly give you an overview that what does it mean by this term CP. So at very first, are the CPs basically shows us the molar specific. I'm just writing here speci molar specific heat. Both of these terminologies, this C actually presents us the molar specific heat. Okay, now this P, that probably means that here, let me change my color of the pen. Here it actually shows us that the pressure, P denotes as the pressure, is constant. And here V tell us, V actually denotes the volume, and volume is kept constant. Now what happened to the equation or the system when pressure is constant, volume is constant, and the condition is molar specific heat? If you are still not known about what does it mean by molar specific heat, so you must get into our previous videos where you can find out what is molar specific heat, what is a specific heat, what is other types of the specific heat. At very first, you might be thinking that, okay, this is the constant volume, this is the constant pressure, where these all terminologies are derived from. So if you are have gone through our previous videos, you might be known about first law of thermodynamics. Thermo, and just I'm writing thermo, just keep this in mind, this is thermodynamics. Now what is the equation of thermodynamics? The basic equation of thermodynamics is change in Q equal to change in U plus W. Here Q shows us the heat provided to the system, U shows us the existing internal energy or change in internal energy, and this W shows us the work done. At very first, if you keep the constant pressure, let's first derive the condition for constant pressure, or let's just write it as constant pressure. At very first, you might be known about W, that is equal to P into del V. Now the derivation, exact derivation, detailed derivation, I'm not going to cover in this video since these all things are the terminologies that are used in our previous videos. So just go through those previous videos and I'll drop down the link of those videos in my description box as well. So keep this in mind that in constant pressure, the work done becomes P, the constant pressure, and V, the volume. So the equation, final equation would be change in Q into change in internal energy plus P del V. Now tell me one thing, that what do you think? What is this condition? Which process does it actually shows us? So this process is actually the process that we cover in isobaric system. Isobaric isobaric system. So this is the isobaric system's equation. Now second term that we use is constant volume. Now we all know that if there is the constant volume, so there isn't any change in the work done, because what is work done? When this piston actually moves upwards or downwards by reference of the heat provided to the system, or we just are actually creating a sort of least amount of the weight on the piston, so it moves, actually gradually moves upward because of internal energy. So this is called the work done. And if we are keeping this volume at constant space, so there isn't any work done. So all the heat provided to the system turns into the U, the actual internal energy. And this situation, we often see this situation in isochoric system. Again, this is a detailed lecture system. Well, I have covered the basic concept of how it becomes PV, not how it becomes PV, but actually how work done is kept constant, and how why we are show this and all. So this is how we actually delve into the situation. Now, if you have gone through this equation in depth, so let me change my color of the pen again. Okay, so you might have seen that Cp is actually being subtracted by the Cv. That probably shows us the situation where Cv is termed as the least value, or what we can say lesser than the Cv. And this is actually a condition that Cp is always greater than Cv. And for that, we do have a conceptual situation. First, note down this term, or note down this line, that Cp is always greater than the Cv. Okay? Now let's see that why it actually happened. Let me use okay. To understand this situation, first keep this in mind that okay, we are going to suppose some values. Just suppose for a while that u1 is equal to 100, then u2 is equal to 110. Of course, this would be in joules in both of the situations. And now what we have to do, we have to see that what makes this u1 delve into u2. Now, at very first, if you look into both of the situations, let me compare both of the situations. Here I'm writing Cp, here I'm writing Cv. Now we know the equation for the Cp, what it is. The change in Q is equal to change in W plus PV, del V. And what is the equation for this? Change in Q is equal to directly change in U, right? Okay, so at very first, we are given a situation where we have to see that which of the equation achieves the CV, the U2 value, the 110 value, more frequently and more efficiently. At very first, if you look into this situation, so let's say for a while that we have to achieve the first situation, we are providing 20 joules to the system, by reference of which this 20 joules is dividing itself into first Q1 and then the P1 situation where work will be done. Okay, so if we'll see, let our very first provide 10J, since the change in internal energy, what it is, 110 minus 100. So we have to increase our value up to 10 joules. So let's just consider 10 joules in this situation. Let's see that 5 joule is actually the heat provided to the system. In addition, the 5 joule work is heat is actually used within the system to do the work done. Since whenever we are talking about the laws and all, so we all know that there is some sort of heat that is used by the system to do the work done. So here, if we look into the final result, so we aren't achieving the exact value. We are having 5 joules, but we actually have to gain 10 joules. In this situation, if I'll provide 10 joules to the system to achieve the value, so it will directly turn into 10 joules. Okay. Then secondly, if we have to achieve the 10 joule in this situation, so we must have to provide 20 joule to the system. That will turn itself gradually into 10 joule plus 10 joule. So now we achieve the situation of 10 joule. So that's why the Cp is always greater than the Cv. Since we have greater value of the heat provided to this system, because we have to provide 20 joules to the system, so 10 joule will be utilized in the work done, and the 10 joule will be the amount achieved. And here we only have to provide 10 joule to the system, since everything is directly converting itself to the internal energy. So this is the concept that why Cp is greater than the Cv. Now let's again look into the situation. Now we do have this R. What does this R specifically shows us? So this R here is basically the constant, universal constant of gas, and this, well, its value is about 8.31, and then again its function or the unit would be joule into mole, the molar specifics one. Joule into mole. Okay, so here I did a mistake. It's joule per mole dot Kelvin, and this is called universal. I'm writing here universal gas constant, UGC. Okay, so this was all about today's lecture. I hope that you get it, and all the concepts that why each and everything is happening is covered there. And stay tuned for the future videos. Thank you.